Welcome to the engineering design presentation from the team of Bern Formula student from the University of Applied Sciences Bern. This part is about the low voltage electrics. My name is Felix Sarbach. I am the CTO of the Bern Formula student team. And with me is Manuel Lindauer. He programmed the central computing unit and played key role in make or buy decisions in this year's car. After this brief introduction, Manuel will explain how we made our decisions and a few aspects about make or buy decisions. Afterwards, I will be talking about our sensor choices, how we evaluated our sensors, and what we would do if we were on a minimal budget for our sensors.
Decision making. At the beginning of the season, we would assess what has worked well, which components or parts need improvement, and which components should be replaced or remade or further developed. We also take the size of the electro team in consideration to see how much manpower we have. Based on these factors, we decide what developments we should tackle. Make versus buy. This race car build is all about developing and creating components. Since we are all students, we want to, of course, learn one or two things. But the development process can be very time consuming because errors are easily made and not so easily found. Time is also very valuable in a Formula student season. And for that reason, it is impossible to develop every component yourself. The incentive to develop components is for one, obviously the money which can be saved, and of course also a bit of pride seeing a working component you developed yourself. Our first and most important priority is the reliability of the components we are using. We constantly have to assess if a component is worth developing by ourselves or if there is an easy to use, worth the money and reliable solution we can buy. Another good reason to buy components is the rules conformity. With self-made products, it is often hard to make it rules conform. For this reason, we have decided to buy all the high voltage parts, for example. And with this, we move on to the next slide. We have bought solutions for our central control unit, the speed code, all the high voltage components, like I mentioned before, and the battery management system. The decision to buy the VMS was based on the small dimension, the simplicity of the device, and the price. Another good example where we decided to newly buy instead of developing ourselves are the CAN bus cables. In previous seasons, we assembled the CAN bus cable ourselves, and we always had problems with the shielding of the cables. So we had issues with the electromagnetic interference. Plus, it is quite a time-consuming job to do. With the new bought solution, it works perfectly, of course, and it saves us a lot of trouble and also time, which we can use to develop other stuff. For this season, we also decided to upgrade from self-made to bought inverters. Similar to the CAN bus cable, the old inverter was not running reliable. This was a big step for us, but it surely is a good investment, which will allow the team to progress even more. We now have a fully functional inverter with no EMV problems. I think it is important to have as many reliable and working components in your car so that the self-developed components can be tested properly. The components we developed and assembled ourselves are the dashboard, the battery safety board, the brake system plausibility device, the tractive system active light, the brake light, and all the sensor boards and general purpose input and output boards. The sensor board converts a signal from the sensor to an analog signal, which then can be transferred to our CCU, the speed code, through the CAN bus system. The GPIO converts the signal from the CAN bus to a specific output. We have had a very good experience with these self-made and self-developed components.
Thank you, Manuel. Given that the car is not an easy system, I tried to distinguish three different types of sensors. First of all, the rules-mandated sensors. These are, as the name says, given by the rules. Most of them are hardwired and are for safety critical signals. There's not much sense in talking about these since the room for improvement in these areas is very small. But in the car sensors, there's a lot about to talk. In our case, this is a gyrometer and accelerometer, brake pressure sensors, cooling system temperature sensors, steering angles, and a few more. Furthermore, we have some extra sensors that are not on the car for all the time. Most notable about this one is the eye tracking of the driver. The largest challenge on the car sensors and the auxiliary sensors is the integration into the whole working system and to pre-evaluate before we use the sensors what the work and information ratio is, that we can gain the most information in as little work as possible. The gain does not only have to be for the current car, but it can also be in the form of data for the next car. The evaluation of the car sensors. Generally, they can be divided, or there are 5 main goals that an extra sensor in the car should or try to fulfill. First is an improvement in the drivability. An obvious example is a steering angle that we can make an electric differential, and in a left turn we can turn the right wheel faster than the left one. A second goal is for driver car handling feedback, that we can judge the abilities of the driver and how the car reacted to it. Furthermore, a main goal is always to improve the safety and reliability. That can be in shape of redundancy, but as well to avoid overheating and protect several circuits. Also, for data acquisition about the car or the driver, and also as engineering review to see if our calculations or estimations for the car's properties are correct. An example for that would be the efficiency of the cooling radiators to evaluate for future years if we have to make the cooling larger or smaller. Special this year is that will do tests with the driver's eye tracking goggles. This is an auxiliary sensor which is not directly mounted to the car, nor can the data be evaluated very easily, but rather after a drive the data has to be combined with the track we drew and the driving goggles with the view of the driver. That whole process can be very time intense, but it is also difficult to pre-evaluate what the information or the information gain to work ratio is. That's why we chose to test this system. The main goal for us is to evaluate the drivers in a better way and to give them some very easy training that we can review what the driver saw and did. A part of this should be also handled in the driver interface. That's why I'll keep this part very briefly. And to the last part, what if we had a very small budget for the sensors? In hindsight, it was a great decision to make the sensor boards. They are rather cheap boards, cost about €6, and it can manage two sensors, any type of analog returning signal. Then it will put the signal in a form of CAN bus data to the central computing unit. That way we have a large variety of sensors we can choose for, which also means the more sensor we can choose from, the cheaper sensors we will find to buy. Thus, these boards give us a simplicity in the whole system, a reliability because we have less analog lines in the car, and we can save money. If we would have to save even more money, then we'd start to differentiate what sensors are for driving the car at the moment, for example the steering angle, which does give us a speed or a time gain, and what sensors are for data acquisition, for example an additional cooling temperature sensor to evaluate the efficiency of the cooling system. By differentiating these two types, as well with the 5 goals of the sensors I mentioned previously, it should be possible to evaluate how important each sensor is and save money on them. That's it for the engineer design presentation. Thank you very much.